testando. Tá funcionando. Hi.
Hello.
Hi, how are you? Do you hear
Hi.
me okay?
Yeah.
Yes.
Hello.
Uh, we are finishing up here some little details. We are going to start soon.
Good.
If you want to share your screen,
Hi.
coloca a tela dele que eu não estou enxergando.
Okay. Is it seen?
Yes.
Good.
Yes. Is everything okay? So, uh,
Okay, good morning, everyone. I would like to introduce the Professor Dmitry Kerner, Gurion University, Israel. He talk about characteristic-free approach to left-to-right equivalence of maps from K to the N to K to the P. Okay,
Thank you very much. Thanks. It's pleasure to speak. Yeah. Do you hear me? Is the connection is okay?
Yeah.
Good. So let's start. I will speak about these maps. So let's start with the prologue, with the very old history. So one of the origins of singularity theory was the study of these maps. Yes, initially it was when K is real or complex numbers, and the maps they were uh, infinity or real or complex analytic maps. Yes, this is how Whitney initially thought it should be done, and this is how it was done by Mather and others. And these maps they were studied up to right equivalence or left-right equivalence or contact equivalence. Yes, everybody knows. And the first steps in this study, there were the finite determinacy of such maps, the theory of unfoldings, and the theory of stable maps. Now, what is interesting is for me, most of the definitions they were of algebraic nature. They could be stated over any field, K is any field. But the proofs they heavily used analysis. Yes, integration of vector fields and differential equations. And at least for me, it was irritating that there should be algebraic formulation. Now, yes, this is what I wanted to say. Yes, and in the last 40 years, many results on the right and contact equivalence were extended to any field, any characteristic. Yes, sometimes with some additional assumptions, sometimes with some restrictions. And I will mention just few names. So it's Gerd Martin Groyle and all his groups and collaborators, for example, these people. And recently I did also some work with Heinrich Belitsky. So the right or contact equivalence, they are quite understood in the arbitrary characteristic by now. So of course there are questions. And the K equivalence, yes, the left-right equivalence, is essentially more complicated, and it is the equivalence for this map. Yes, it is the most important equivalence for this map. And to the best of my knowledge, nothing has been done about the formulation of this equivalence, even in zero characteristics. Yes, not speaking about positive characteristics, and I will speak about this. So this is what I will be talking about. And then feel free to ask questions. Hopefully, I have not too much to present, and I will have time to answer everything. So let's start. Well, from the very beginning, maps and equivalences. So K will be any field. For example, if you prefer real or complex numbers, or maybe a finite field in positive characteristics, or maybe p-adics, yes, or whichever field you would prefer. And take the germ. Yes, the germ of the affine space at the origin. Yes, just the germ I will take formal or analytic. So more precisely, to specify the germ, I will explain what is the local ring. The local ring is either the ring of formal power series or the ring of locally convergent power series. And to speak about locally convergent, of course, I assume that K, the field, is normed and complete. For example, real or complex numbers. And there are many other fields that have norm and that they are complete. And then consider the maps, yes, exactly as in the classical case, from the germ of Kn to the germ of Kt. Now fix some coordinates in the target, yes, as one usually does, yes, y1 up to yt, and then every map is presented just as a vector valued function. Here is the function, here is its coordinates, yes, its entries, and so this presentation fixes, using this presentation, we can identify the set of all the maps with this free module. Yes, this is the free module over the OKN. Yes, direct sum equal this. Actually, we consider maps of germs, so every function must vanish at the origin. Therefore, here there is the maximum ideal. So from now on, when I will speak about maps, usually I will identify them with this vector value notation. Well, here is the right equivalence. Yes, right equivalence means we change coordinates in the domain. So these are the automorphisms of the domain. Or if you prefer, more precisely, these are the automorphisms of the local ring. Yes, the ring of formal power series or of analytic power series. And the automorphisms are supposed to be k-linear, yes, exactly as in the classical case. Just the coordinate changes. And these coordinate changes, they act on maps, yes, just by the composition on the right, exactly as in calculus function. Similarly, we'll speak about L equivalence. Yes, now we take the coordinate changes in the target. Again, these are the automorphisms of the local ring in the target. Also, it would be key here. And again, they act on the map by the composition on the left. And then the A equivalence is just the direct product of the two groups. There are two huge groups. Then we take the product, and here is how it acts on them. So by now I did not say anything new, of course. Just one general remark. So here, from the very beginning, I restricted to some very particular rings. Yes, rings of formal power series or analytic power series. Most of the results they hold for more general rings. For example, we could take a quotient by an ideal. It means that we consider maps not from the smooth germ, but from some singular germ. Yes, or we could do it in the analytic case as well, or we could consider the algebraic power series. Yes, so the power series that satisfy some polynomial equation is especially important in algebraic geometry. Yes, and most of the results they work for much more general cluster. Well, and now finally determinant. Yes, this is the cornerstone of the study. Yes, so the question is when is, so let's take the group. Yes, for example, the right equivalence, or left-right equivalence, or the contact equivalence. And the question is when is the group orbit large? Large in the following sense. So we take the group orbit, and it must contain some neighborhood of F. So this is the neighborhood. Once again, this is the set of all the maps, and this is the maximal ideal to the power d. So basically, these are the maps that vanish at the origin to the order at least. Yes, so such a phenomenon, it would say that your map is stable under higher order perturbations of order at least. This is some minimalistic version of stability of yes, and of course it is very important and it's a very useful property. Or equivalently, one could say that if d minus 1 jet of f coincides with d minus 1 jet of some other tilde, then f is equivalent to tilde by our rule. Now, this is the classical formulation. Actually, more natural and a bit more general is what is the largest ideal inside our ring, such that the orbit contains this neighborhood. So sometimes the natural ideal that comes into your hand is not the maximal ideal, but some other ideal. Yeah. And then once you have determined this largest ideal, then you could ask maybe what is the smallest power of d, such as f to the power d fifth inside. But usually this is a more natural question. Now the traditional approach to such questions to check how large is the orbit is to study the tangent space. So, for example, for the right equivalence, the coordinate changes in the domain. The tangent space, the actually extended tangent space, is these are all the vector fields, the germs of vector fields in the origin or the derivation. Yes, they are k-linear. So again, when k is real numbers or complex numbers, you have just a completely classical object. Yes, for example, if your function is a scalar function, then here you will have partial derivatives, and you will get the Jacobian ideal. Now, this is the extended tangent space. Here are just all the possible derivations. Sometimes we take the tangent space, which are derivations, those derivations that vanish at the origin, or those vector fields that vanish at the origin. So these are the tangent spaces for the right group, the group of right equivalences. And then similarly, one has the tangent spaces for the left group. Yes, these are the, again, derivations in the target. And also here you have the extended version or the ordinary version. And then the tangent space to the left-right group is just the sum. Yes, both in the extended case and in the ordinary. And then there is the old and classical theorem, yes, that was proved. Actually, it was a long way to achieve the best bound. Yes, everything is over real complex numbers. And the statement says that if the tangent space is large enough in this sense, if x to the power d times the depth inside, then also the orbit is large enough. Yeah, so here you have d, here you have 2d. It's not a mistake. You cannot significantly improve with 2d, unlike some other equivalences. This was the really groundbreaking result, because it shows that if you work with such germs of maps, then actually you can check everything only up to some kind of order. Yes, if you want to check that you can bring the map to some particular form, or that two maps are equivalent, it is enough to verify only up to some kind of order. There are similar results for the right and contact equivalences, and in each case, the proofs they use integration of vector fields. So from the very beginning, somehow all this was very deeply rooted in analysis, even though the statement is completely algebraic. Well, and so I wanted to extend this to the arbitrary field, and so here is the statement. Suppose K is infinite field. Now, if the tangent space satisfies, so if the tangent space is large enough in this sense, so here you have a contribution from the right part, the contribution of the left part, and it must contain the a square, a is the ideal, and a also appears here. Then the orbit is larger this sense. So you can compare these two results. You see that here you have a square, here you have equal 2. Yes, they are very similar. Now, this condition is a bit irritating. It looks complicated, but I could not simplify it. in many cases, this condition is weaker than this condition, the assumption. And then the statement is even stronger than the initial. But in general, I could not simplify it. This is the condition. And just one remark. So this assumption that K is an infinite field, I hope that one does not need it, but currently I need it inside the proof. This is a technical assumption. Yes. Good. Now, maybe any questions? If there are no questions, so let's proceed. And then people try to strengthen this result, and they could not strengthen in this form. But then Bruce, Duplessis, and Wall, they came with a very nice idea, yes, that they could do in a bit different direction. So instead of the extended tangent field, tangent space, or just tangent space, one could consider the nilpotent tangent space. Yes, these are all the derivations that vanish at the origin, not just to the first order, but at least to the second order. So these are the derivations in the domain, these are the derivations in the target, and then the nilpotent tangent space to the A orbit is the sum. And here is the statement. So if the nilpotent tangent space contains these P's, then also the orbit contains. And now this is certainly this is the best possible. You see, it is the same D. One could not hope for a better result. And again, all this was over real complex numbers, and the proofs used integration of hello. Hello? Can you hear me? Is the connection okay?
Yes, it's okay now.
Okay, good. So the proofs use integration of vector fields, and somehow it was not clear how to prove such things over an arbitrary field. But well, now it's able. So here K is any field, not necessarily infinite. And so again, suppose the nilpotent tangent space contains this x to the power d, and now there is assumption on the characteristic of the field. Either characteristic is zero, for example, real complex numbers, or the characteristic is large enough. It is 2d minus the order of the map. Then the orbit contains exactly the same piece. So this extends to this classical result, and more or less it is the best that I could do. Yes, the assumption on the characteristic is important. Without this assumption, there are counter results. Okay. So this is about the finite determinacy. Now let's proceed to unfolding. If there are no questions, so unfolding. Let's start. András, could you switch off your microphone? Oh, okay. So let me recall the definition. Yes. So suppose we start from a map. K is any field. Yes, a map, and an unfolding is a map from the larger space to the larger space. Yes, we add several additional coordinates. The map of this form. Yes, where ft is just a deformation of f. And accordingly, we extend our ring. Previously, it was just the ring of the form of our case. Now we introduce new variables. Or if you work with analytic power previously we worked over K, now we will work over this larger K, capital K. So it is not a field, it is a ring. And accordingly, yes, if we introduce new variables, then we also extend our group. So now we have the group of families of coordinate changes in the domain. This is RT, right equivalent. So these are the automorphisms of this Kn plus R over Kr. So what means over? It means algebraically, it means that they are capital K linear. Or geometrically, they preserve the fibers of this projection. Oh, sorry, so it should be Kr, not Kt plus R. Kr. So this automorphism, they preserve the fiber, they act fiber-wise. Similarly, for the left equivalence, we have the families of automorphisms in the target. And then, as before, the A equivalence is the right times left or left times right, as you wish. And then the definition and unfolding is called G-trivial, where G is one of these groups, if it can be trivialized. Yes, if an element of the group, when acting on the unfolding, converts it into this F0 and P. This is the first part. And then the second part, unfolding is infinitesimally trivial if it is trivial at the tangent level. So if when we take partials with respect to T, that's all the possible partials, all these belong to the extended tangent space. This is completely classical definition, and you see it works over, at least it can be stated over any field. Here, there is no analysis inside. And now the lemma, this is called lemma of some latent type. I don't know who is the author precisely, or when you have real complex numbers. So an unfolding is trivial even only if it is infinitesimal. And it certainly is helpful when you have some deformation and you want to trivialize it. It is enough to check if conditions at the tangent level. And well, unfortunately, it does not hold in positive characteristics. It is classically known. Yes, if the characteristic is P, then, for example, this very simple unfolding x to the power n plus P to the power P times x. And here, when you take the derivative with respect to T, you just get 0. Unfolding is, of course, not trivial. So, then one could think that there could be many other abstractions, but actually this is the only abstraction. Any possible abstraction will be necessarily of this nature. So let's take the definition. So an unfolding is called K-wild if it is equivalent by the corresponding group to this form F0, yes, the initial term, and then T to the power D times Fd, and then maybe higher order terms, where this D, it is divisible by the characteristic. So in zero characteristics, you have nothing like this. This appears only in positive characteristics. Yes, and of course, and this Fd, it does not belong to the tangent space. So you have no hope to eliminate by any transformation. And then the lemma is that if F is trivial, then it is infinitesimally trivial. This holds always without any assumption. And then if F is infinitesimally trivial and not K-wild, in this sense, then F is trivial. So this is the very natural generalization of the lemma of some latent type. Yes, and it seems, at least to the best of my knowledge, this was not known. No, it is this lemma is very simple. Now let's move further to the versality. So an unfolding is called G-versal if any other unfolding is the equivalent to a full vector. Yes, so namely in the formula, so some other unfolding is the equivalent to this form F, and then some function of T tilde and here. So universality means that this is the most inclusive unfolding, that everything else comes from everything else is contained. And as always, it is hard to check something on the orbit, and then we switch to the tangent space. So an unfolding is called infinitesimal reversal if we have some sort of universality at the tangent level. So we just differentiate with respect to our parameters, the time at time 0, and the span of these derivatives plus the tangent space, extended tangent space, is the whole. So this is the first version is the local version, the second is the infinitesimal version, and then the question is about the relation of the local and infinitesimal, and the unfolding is reversal if and only if it is infinitesimal reversal, and this holds for any case. There's no restriction, and for real complex numbers, this is very classically known. Martinez from 76. By the way, are there any questions? If there are no questions, so let me proceed. And then the next topic is the stability. Yes, the stability, stable maps, they were the very first to be studied. This was the motivation of Whitney to go into this direction. So a map is called stable if any unfolding of it is A-trivial. Here the group is the friend group. So whichever way you deform it locally, the deformation will not essentially change the map. Yes, and there are many of such maps. And as always, to study it, we switch to the tangent level. So a map is called infinitesimally stable if its unfolding, if its tangent space is the whole space. You have an extended tangent space. So these are the classical definitions, I don't know, of Wiki, of Manner, I don't know who first gave these definitions. And then the question is always what is the relation of the local stability and the infinitesimal stability? For any case, for any field, f is stable if and only if it is infinitesimally stable. Yes, and this infinitesimal stability can be stated in various other ways. For example, the tangent space to the universal deformation is 0, or the codimension, the H codimension is 0. Yes, and this is just the extension of the classical results of Manner. Yes, the stability can be checked infinitesimally. And finally, the question is what are the stable maps, how to construct them, how to distinguish them. Here is the statement. So if two maps are stable, yes, and they are K equivalent, then they are also A equivalent. Another formulation, if the two maps have the same local algebra, then they have isomorphic local algebra, then they are A. So in the real complex case, these are the classical results of Manner, and again the proofs used some analysis, integration of vector fields, some analysis. And now it is for the case of infinite fields, the proof result analysis, purely algebraic. And as before, I do hope that this assumption infinite is not necessary, but currently I need it. I could not do it without it. Well, and there were no questions, so I finished too early. Sorry. Thank you much for your attention.
Okay, let's say thanks for Professor Dmitry for a very nice talk. And there is some questions from the people here. Online, Professor, there is some noise in your microphone. Then you cannot hear you in the good way.
András Némethi, please, your microphone is out of order. We cannot listen to you. We are trying to talk to you since the beginning of the week. It's impossible to listen to you, Professor Némethi. Please, write in the chat. Não, é o Némethi, não é o Dmitry.
Professor Némethi.
Mas não, é outro nome. É o András Némethi, eu conheço ele. Dmitry, we're sorry, there is a problem with the sound of Professor András Némethi.
I know.
So we can't listen him since the beginning of the week, but he didn't realize it yet. Sorry.
Wait, you say you could not hear me?
Yes, we can hear you perfectly, but the problem is with his sound, not with your or other sound. Understand me? I asked him to write in the chat, but he didn't.
Maybe we can, Andras, maybe you can formulate the question by chat. No?
Pergunta se tem outras questões.
I would like to some question for Professor Dmitry, and you speak about unfolding of triviality. You introduced the notion of K-wield, right? Yes, and can you hear me, Professor?
Your sound is out of your, is out now, Dmitry. Please, Kerner. Your sound, yes. Open it.
Yes, okay, and now.
Yes, that's okay now. Thank you.
Yeah. Can you,
Yeah.
can you hear me, Professor?
Yes.
Yes, we can.
Yes. When you speak about triviality of unfoldings.
Yes.
Yes, there is definition K-wield. It's can you have some interpretation of this notion or some example in order to try to?
Yeah. So here is yes. So this is the interpretation, and so the problem is that in the positive characteristics. Yes, for here. Yes, am I sharing properly? Do you see the slide? Do you see the slide?
Sorry?
Hello?
Yes.
Do you see my slides?
Yeah, yeah.
Yeah. So you see here, you might have something which is absolutely non-trivial, but it is multiplied by t to the power of t. Yes, and then because of the positive characteristics, you cannot see it when you differentiate. That's the problem. This is the traditional curse of positive characteristics. So in zero characteristic, of course, you would see that it is non-trivial, but in positive characteristics, you do not see it. So this is and one could expect that there could be various other abstractions of positive characteristics, but it happens that this is the only abstraction.
Yeah.
So this is the only thing to be afraid of.
I see. Thank you.
Pleasure.
Okay, if it's not, there is not more question, let's say thanks to the speaker again, please. The next talk, it's 10 minutes and 9:15.
Hi, András.
Do you hear me now?
Now it's perfect.
Well, because I switched, I
Uh,
changed the computer. I know I have a different laptop, and so now it's
Yes.
okay. The previous was not. I was worried that what to do. So now you hear me.
Hi, András.
Yeah.
Now I
So
can
sorry,
hear
but
you and the
now
sound
it's
is good.
Okay,
Now
then
Oh,
it's
thank
I
okay.
try now to
Good,
transfer
very,
everything to
very
this
good.
laptop.
Welcome.
It's very nice.
Okay. I'm
Very
sorry
good.
for all the troubles what I
Don't
caused,
worry.
but
It's
I was
part of
worried
the
what to do.
internet.
Yeah, I was worried because your talk will be the next
Yeah.
Yes.
And then if you don't hear my questions, and you you will have, then I cannot give the talk. Yeah.
Yeah.
Okay, then I try to move my files to this computer, and then okay.
Good.
So thank you very
Very
much for
good.
the
Yeah.
Very
and then
nice.
okay.
And
I'm
maybe
glad that everything is okay now. So,
Yeah.
and
so you
maybe
had many questions to many speakers, but
Actually, I all that I wanted to ask, and I'm sorry.
it's okay. It's okay.
Yeah.
Dmitry
Okay.
is still there. I think I don't see the organizers.
The
Okay, so
organizer
I
is out a
see
little
how
bit.
I can do the no the okay. Thank you. I still
That's good.
Very nice. Very nice. We will begin in few minutes. Okay.
Your sound is a little bit low, Marcelo.
Sorry.
Your sound is a little bit low. Maybe mine.
Let me change the microphone.
Okay. Okay.
Can you hear me now? Cidinha?
Yes.
Melhorou o
Now
som?
it's good.
Perfeito. Ótimo.
O Rodrigo já tá online. Salomão? Yes. Você quer falar com ele?
Let's, so Rodrigo, so you are ready?
Yeah, I'm here. Can you hear me?
Yeah, but the sound is.
Not so good. And now?
Uh,
Is that okay?
can you? It's still is not. It's not seems.
Oh, can you hear me better now or not?
Yeah, it's.
May I share my screen?
Yes, please.
Okay.
So, okay, let's proceed with the next speaker is Professor Rodrigo Salomão, the University Federal Fluminense in Brazil, and he speak about the on the classification of fibrations by singular curves on unirational surface. Okay, Professor Rodrigo.
Okay, so first of all, I would like to thank the organizer for the opportunity, especially because I know that it's not so common to have people talking about singularities in positive characteristics. So let me, sorry, turn it on my camera. Sorry. Well, I would like to start the talk recalling an important theorem of algebraic geometry, which is the Bertini's theorem of variable singular points. Okay, and it says that almost all fibers of a dominant morphism between smooth algebraic varieties over algebraically closed fields of characteristic 0 are smooth. However, this result is no longer true when we pass from characteristic 0 to positive characteristic, as was discovered by Zariski. And now we give an easy example to see this problem. So let us consider K be an algebraically closed field of characteristic P, and a map from the affine plane. Let me just put here a pointer. Sorry. Oh, now I have a pointer here. So we have. Can you see my screen or not? I get
not.
sorry.
Can
Let
you share
me
again?
try.
Yeah.
So let me try to put again. Sorry. So now it's working. Okay. Well, we consider the map from the affine plane to the affine line given by this polynomial here, and the fiber of this map is given by the affine plane curve given by this polynomial here. Okay, so if we apply the Jacobian criterion, we can compute the possible singular points of each fiber, and we can see that the singularity of this fiber is exactly this point here. Okay, so in this way, we have a counterexample. This is a counterexample to Bertini's theorem, and it's possible to show some interesting connection of this phenomenon. So the first connection is with the extension of Henrique's classification to positive characteristic that was done by Bombieri and Mumford. And the second interesting connection is with arithmetic geometry. And in this way, this kind of fibrations can provide also examples of pencils of singular and non-classical and strange curves in P2, in the plane curve, in the plane space. Okay. Another interesting connections is with counterexamples of Kodara vanishing theorem. It was discovered by Mukai and Zhang. And the last interesting connection is with isolated singularities with infinity Milnor number, as was discovered in a joint work with Jefes and Rodriguez. So I'm sorry, I forgot to say that. Really sorry. It's a joint work with João Helder Rodrigues and Raylon Carvalho, and it's part of PhD thesis of Raylon Carvalho. Okay, sorry again. So let's go ahead. Well, so after to show you some nice, some interesting connection, it's natural to ask if it's possible to classify this phenomenon. So in order to answer this question, we established some definitions. So for us, a fibration by curves is a dominant morphism between integral and complete varieties, such that the general fiber is smooth. Integral curve, the total space is smooth after eventually restrict the base to a dense open subset. And if we put the word non-smooth or singular together with a fibration, we just mean that it is a dominant morphism, such that the general fiber is non-smooth or singular. Okay. Well, we also say that two fibrations are said to be equivalent when it's possible, when we have birational maps between the total space and the base space, okay, such that this natural diagram commutes. This one. Okay, so we can see that we have equivalent for fibrations when their genetic fibers are isomorphic. So the first approach to the classification of such fibrations was introduced by Storr, and to understand what was done, we will show you, we will say the special feature of genetic fibers of fibration by singular curves. Okay, so if we have a fibration by singular curves, if you want to study fibration by singular curves, we want to have fibrations with some horizontal divisors containing the singularity of the general fibers. On the other hand, the horizontal prime divisors corresponds to points of the closed points of the genetic fibers, and the horizontal prime divisors containing the singularities of the general fiber of a fibration by singular curves corresponding exactly to regular points but non-smooth, where we say that X is a regular point when its local ring is regular, and we say that X is non-smooth when there are singular points on the extension of the genetic fiber to on the base extension of the genetic fiber to its field, to the algebraic closure of its field of constants. Okay, so the idea used by Starr was to classify fibration by singular curves, classifying their generic fibers. Okay. On the other hand, I would like to give you another approach which works over surfaces, and it was introduced locally by Bombier and Mumford in the Enriquez extension classification of surface in positive characteristic, and was done globally by Takeda to construct counterexamples of Kodare vanishing theorem, and Shimada to describe supercuspidal families of curves on surface. Okay. Well, to understand this approach, I would like to show some example. A example. So I will use exactly the example introduced previously. Okay, so we have a fibration from the affine plane to the affine line, given by this polynomial here. Okay, so it is a fibration by singular curves, and if we use a smart, if you introduce smart new variables like this one, so remember that the fiber here is a plane curve given by the polynomial x squared plus x to the p equals to t, or equivalently, x to the p minus t equals to 0. Okay, so if you introduce new variables like this, so we take the capital T equals to the p root of the small t, and if you take capital Y equals to the p root of small y, okay, and capital X equals to the small x, we will have this fiber. This fiber can be written in the following way. So y up to the p square plus x to the p minus t. Oh, sorry, here is to the p. Sorry, and t up to the p. Okay, equals to 0. So if we use characteristic p features here, and we will have y squared plus x minus t up to the p equals to 0. And in such a way, we will obtain a fibration given by this polynomial whose fibers, which are exactly this one, are smooth. Okay, so if we do this base extension exactly with the introduced new variables, we will obtain a kind of smoothing of the previous fibration by singular curves, which is exactly this one. Okay, so a nice question here is to understand what is the property characterizing the pre-image under this map of the horizontal prime divisor containing the singularity of the generic of the general fiber of this of the fibration F. Okay, so it can be answered by considering a vector field. So firstly, this horizontal prime divisor is given by y equals to 0, and the pre-image under this map is also equals to capital Y equals to 0. Okay, so to understand what is the nice feature characterizing this new horizontal divisor, we consider a vector field like this. Okay, and we use some vertical lines like this one. Okay, so these vertical lines can be, we can draw them here in blue, okay, like here. So we have some vertical lines. If we apply the vector field to the equation of these vertical lines, we will obtain 0, okay, and for every line like this, okay, it will be vanished by these vector fields. In this way, we say that these lines are invariant under these vector fields, okay? And if we see these points of intersection between the lines and the horizontal, the pre-image of this horizontal divisor, we will see that we have exactly a tangent between these lines and the fiber of the smoothing F1. Okay, so in this way, this horizontal divisor is called by the tangent divisor, okay? The tangent divisor, okay? And to finish this example, I would just want to say that this affine plane here, X, can be seen as a quotient of this affine plane by this vector field, because this affine plane is the spectrum of this ring of polynomials, which is also the spectrum of this ring of polynomials because of the introduced new variables. And this ring of polynomials is exactly the kernel of these vector fields here as a vector field here in this ring of polynomials. Okay, so in this way, we say that X is the quotient of X1 by the vector field D1. And we write like here, okay? And okay, and this map here is a map induced by the vector field as well. It's called the quotient map. So in general, Shimada proved that if we consider an algebraically closed field of characteristic 0 and a fibration by singular curves F, where X is a normal surface and Y is a smooth curve, then and if X1 is the normalization of this fiber product here, then we can obtain a vector field D1 on X1 such that this diagram here commutes. Okay, this diagram is similar to the diagram obtained in the previous example. Okay, and this map here is the relative Frobenius map of Y1. Okay, but maybe we cannot obtain the smoothing of this fibration by singular curve with just one step, with only one step, but Shimada proved that if we apply this process finitely many times, we will obtain the smoothing, okay, of this fibration here by singular curves. Well, so it's natural to ask if it's possible to use Shimada's smoothing process to classify fibration by singular curves on surface. And we will approach this problem with a particular setup, okay? So we we are going to consider fibration by singular curves f, such that x1 in Shimada's diagram is a rational surface, and such that we can reach the smoothing of the fibration f with just one step in Shimada's diagram, okay? And in this case, since this surface is a rational surface, we obtain that x is a unirational surface. And for this reason, the base curves need to be isomorphic to the projective line, and locally we are exactly with the setup of the previous example, okay? Okay, so another particular setup that we will consider in this work is the following. We note that the arithmetic genus of the generic fiber decreases when we pass from the fibration by singular curves to its smoothing. And for this reason, the simplest case to attack this problem is when the arithmetic general G and G1 of the generic fibers of F and F1 respectively are 1 and 0. Okay, but in this case we have a problem because the equivalent classes of generic fibers of F1 do not determine the equivalent classes of the generic fiber of generic fibers of F. So the next simplest case would be G equals to 2 and G1 equals to 0, but the same problem happens, okay? And the case that we will attack here in this work is the next one, which is G equals to 2 and G1 equals to 1. In this case, the fibration by singular curves is called absolutely elliptic fibration by singular curves of genus 2. And by a bound obtained by Tate, the characteristic must be smaller or equal to 5, okay? However, it's possible to show that absolutely elliptic fibration by singular curves of genus 2 exist only in characteristic 2 or 3, and we will focus our attention here to the case p equals to 3. Well, it's possible to obtain a normal form for generic fibers of absolutely elliptic fibration by singular curves of genus 2, as was obtained by Borges Neto. So here is a normal form for the generic fiber of the absolutely elliptic fibration, and here is a normal form for the generic fiber of its smoothing. Okay, so it's a Weierstrass form because the generic fiber of the smoothing is an elliptic curve. Okay, well, it is also possible to, Borges Neto also proved that two absolutely elliptic fibration by singular curves of arithmetic genus 2 have isomorphic generic fibers if and only if the correspondent elliptic fibrations have also isomorphic generic fibers. So we don't have the problem observed for the first two cases here, okay? By this result of Borges Neto, due to Borges Neto. Well, so in order to describe these fibrations by absolutely elliptic fibrations by singular curves of genus 2, we we need some remarks, and the first one is this one. If we consider E the resolution of x1 in Shimada's diagram, so E is a rational elliptic surface, which means that E is a smooth projective and rational surface. There is a surjective morphism from E to P1, whose general fiber is a smooth curve with arithmetic genus 1, and there is a section of this fibration. Okay. Moreover, there exists a vector field D on the rational elliptic surface E, such that the fibration obtained by the quotient of the rational elliptic surface by the vector field is a fibration by singular curves of arithmetic genus 2. Okay? So in this way, it is natural to ask if given a rational elliptic surface, is there a tree-closed vector field such that the induced fibration is a fibration by genus 2 singular curves? And we can answer this question, and we show that there is such a vector field if and only if the J invariant of the genetic fiber of the smooth of the elliptic fibration is not a cubic power in the field of rational functions of the projective line. Okay. So after to observe this result, we can establish a one-to-one correspondence between the set of fibrations by genus 2 by singular genus 2 curves, with smoothing being an elliptic fibration over a rational surface up to equivalence, okay, and the set of fibration by elliptic curves over rational surface with J invariant being not a cubic power, okay, where this equivalence means that identifies fibrations with isomorphic generic fibers, as I introduced previously. Okay, so if you want to describe, to classify this set, we can use this one-to-one correspondence to classify H via the classification of E. Okay, so in this way, we are in the direction of the classification of E now, up to now, okay? From now on. Well, to do this, we recall an important result due to Kosek and Dolgachev, which says that every elliptic fibration on rational elliptic surface is equivalent to a fibration obtained by blowing up base points of a pencil of smooth cubics in P2, in the affine plane. Sorry, in the projective plane. So another important result in order to stratify the set E, another important object in order to stratify the set E is the Morda-Weil group associated to an elliptic curve. So if we consider a rational elliptic surface and its generic fiber, we have we can look at the rational points of this generic fiber, and this is a group called Morda-Weil group, and it's finitely generated, okay? And Ogizu Ishioda showed that we can compute the rank of the Mordovale group with this formula, where MV is exactly the number of components in of a reducible fiber, FV. Okay. Moreover, the Mordovale group is a birational invariant of the generic fiber. In this way, we can decompose the set E into 9 pieces, where each piece, EI, is exactly given by the equivalence classes of fibration by elliptic curves over rational surfaces with Mordovale rank I and J invariant being not a cubic power. Okay, and in this work we will describe the set E0. That is fibrations with Mordovale rank 0. Okay. Well, to do this, we observe a proposition which is a consequence of results from Ogiso and Shioda and William Lang and other authors, which characterize the possibilities of special fibers and possible special fibers and possible Mordovale groups for fibrations by elliptic curves on rational elliptic surface over algebraically closed fields of characteristic 3, okay, with Mordovale rank 0. And we can show now I show the list to you, and here we can see in each step the possible special fiber and the possible Mordovale group, okay, where these notations of special fibers are like in Kodaira fibers of special fibers of elliptic fibrations. Okay, these notations were introduced by Kodaira, and the geometry in geometry meaning they mean exactly these curves given here in this box. Okay, so if we take this proposition that we have a correspondence, possibilities of special fibers and possibilities of Mordovale groups, okay, of rank 0, and if we contract each special fiber here, we will obtain the possibilities of plane curves that are contractions of each special fiber. Okay, after to take these projective curves, we can combine each two of them, in order to generate pencils of cubic curves in the projective plane. And we take each pencil generated by these contractions, okay, by the combination of these contractions, and we can blow up the base points of these pencils, okay, and making some blowdowns in order with a different group of sections started from different sections. We can see if two fibrations given by two pencils like this may have equivalent generic fibers. So if we do this hard work, okay, hard job, we will obtain that for each special fiber described in the above the previous list, we will obtain a pencil such that the vibration with the prescribed special fiber is equivalent to the vibration obtained by blowing up the base points of the pencil. Okay, so for instance, if a vibration by elliptic curves has a special fiber like this one, then it is equivalent to a vibration obtained by blowing up the base points of a pencil like this one, where D is a nodal cubic and L is the inflectional line, okay, of over the inflectional point of this nodal cubic, okay. And we can do this work for each special fiber described in the previous result, in order to obtain the description. Previously, I need to observe that we have a corollary which says that elliptic vibrations on rational surface defined over fields of characteristic 3 with Mordell rank 0 and J invariant being not a cubic power, with distinct configurations of special fibers, cannot have isomorphic generic fibers. Okay, it is a consequence of this theorem here. Okay, and if we use this corollary, we will stratify again, but now the set is 0 in 8 pieces. Okay, where E0L is described like here. This is the set of equivalence classes of vibration by elliptic curves on rational surfaces with Mordell rank 0, J invariant being not a cubic power, and whose special fibers are like in item L of the previous proposition or the previous theorem. Okay, so if you consider E0L like this one, we can describe precisely the pencils that realize the equivalence classes generating this set. And we do this in this result. So if we consider the vibrations whose special fiber are as the first item of the previous list, then we will obtain that each equivalent class will be given by the vibration, or the equivalence class of the vibration obtained by blowing up the base points of this pencil. And we can do this same work for the other pieces of the stratification of the vibrations with Mordell rank 0, and we will obtain each pencil that realize this set, okay, that describe this set, okay. And to finish the talk, because I think it's time to finish the talk, but I just would like to remark another interesting phenomenon here, which is the description of the vector field, the computation of the vector field. So we can ask this question. So given a pencil in the above list, how can we build a vector field on the projective plane whose induced fibration is a fibration by singular curves of genus 2? So it's a natural and geometric question that we can answer this question with an algebraic approach. And this algebraic approach is the following. We instead to compute the vector field directly on the projective plane, we make we take the pencil, we blow up the base points, and we will reach a fibration by elliptic curves. After that, we change variables in order to obtain a Weierstrass form given by Borges-Neto. There, we can compute the vector fields, and we need to return to the projective plane doing some change of variables and contractions and blowdowns. Okay, so the vector field that answer the problem over the variables over the normal form introduced by Borges-Neto is this vector fields described like here. Okay, and if we take this vector field and contract and we make some change of variables and contractions, we will reach the vector fields with prescribed tangents. Okay, over with the pencils on the plane, on the projective plane, and the list is exactly this one. Okay, so if we have a pencil as in the first item of the previous list, the vector field is given by the vector field d prime, like this one, with a1 equals to x to the square and b1 y to the square, and so on. Okay, so this is the completion of the list, and thank you for your attention.
Okay, thank you, Professor Rodrigo, for the very nice talk. I'd like to ask if there is some question for the Professor Rodrigo and maybe the people online. Okay, if it's not, let's say thanks to the speaker again, please.
Thank you.
Now is we have the coffee break, and you return into 11. Okay, there's some question in the chat, some comment. Okay. Hi, Professor András. Everything is okay?
Well, that's how I can. No, I have a new computer, and I don't know how I can share the. If I just do you see now?
Not yet.
Not yet. So how I can share the? Because I can put on my screen, but I don't know how I share with you.
And inside of the Meet, you can
On the Meet.
use option and
Where?
yes, the right side of the hand, you can click. Yeah. Acho que tá tentando.
András, do you see the arrow in the bottom?
Yes, this one, and
So
yes, and this is.
Yeah. You should choose, maybe it's better to choose a tela inteira, so the whole screen.
Yeah, I don't.
Now you have the choice.
Actually, it's no. I can write, but I wanted to use my. Probably here I can.
Professor, are you hearing me?
Yes.
Maybe you should press the up arrow button.
Up arrow button.
Yeah.
So I don't know. So up arrow.
Oh, is the
on the right bottom at the end?
Is the third? Is the fourth button?
Yes.
From left to the right.
And this is that is I can use the, but I cannot share what is on my screen. It's so.
So take a look in what people here is doing. You see the icon?
Do you see now anything?
No.
Do you see now?
No. Take a look. There is a square with an arrow.
Okay.
Inside.
So what?
People here is going to do, and you just watch. So please. You put so full screen. Okay, then this will appear to you. Share. That's what you have to do.
I just a moment. So. I do the full screen first. So no, could you repeat what you?
Yes, we can. Share.
So could you repeat now?
Yes.
I don't hear anything. So
So you have to press the up arrow button. Are you seeing?
up arrow.
Yeah.
Ah, okay.
Uh-huh.
Okay.
And
Yes.
you press share full screen.
Okay.
Uh-huh.
Yes.
And you choose the full screen and click on blue button, share.
So I will have this up button. Yes.
Yes.
Oh. So I have here a lot of things here.
That's
Oh. So there is the full screen. That is the very first one. That's what you
Yes.
say.
Yeah.
Okay. And what I see here, it's that I have to share.
Yes.
But when I do, Megos, I cannot. Okay.
Okay. Thank you.
So let's see what you see. What do you see?
Now you can.
Do you see now?
Yes, we are seeing.
Oh, sorry for all this. Okay.
No problem,
Yeah.
Professor.
Okay.
That's-
And I
now
have
it's
here
all-
something what I should hide.
Now it's all working on.
Okay. So
Okay,
so then maybe I can start. Yes.
yes, let me introduce you the Professor András Némethi, the Reniy Institute of Mathematics in Hungary, and he speak about introduction to lattice cohomology.
Yeah. So thank you very much, and I apologize for all these troubles here. So I had to take another computer and everything because the other probably also the microphone is not working there. So I would like to first of all I would like to thank for the organizers for inviting me and for giving me opportunity to speak at this conference. And so I would like to speak about the lattice cohomology of normal surface singularities. And actually, there are two types of lattice cohomologies, the topological and the analytic lattice cohomology. And first, I would like to discuss about about the motivation, the original motivation. And after that, the new part is the analytic lattice cohomology. And so let's start then what I mean by analytic and topology. So I start with a normal surface singularity. It's a germ, yes, over the complex numbers. And we have two types of invariants, analytic invariance and topological invariance. What I mean by the analytic invariance is the local algebra, basically. And if I want to find or to introduce some, say, analytic invariance, I have to use either the local algebra or I have to go to the resolution, using the resolution some coherence shift and cohomology and this type of invariance. When I speak about the topology, what is on the right-hand side of, yes, on the page, I consider the link. And if the, so I embed somewhere, I consider a very small sphere, I consider the link. And this link is if the complex dimension of the germ is n, then this is a, and if it's isolated singularity, then this is a oriented real manifold of dimension 2n-1. So in all our discussion, we discuss about surface singularities. In this case, the Lx is a oriented, connected, closed Riemann-manifold. When I speak about the topological invariant, I want some topological invariant of this Riemann-manifold. So what is some connection between these two? That is given by the resolution. If I take, say, a good resolution, I consider the exceptional curves and the irreducible decomposition the exceptional curve, these are the EVs, then this gives a lattice, and then gives the intersection form of how they intersect each other, and then the self-intersection, and that gives also the resolution graph. And the resolution graph somehow is the combinatorial data about the resolution, and also it gives a graph. And if we consider this graph as a plumbing graph, then the Plum's three-manifold associated with this graph is the link. So somehow the link is the same as the resolution graph. So we can say that the topological invariants are basically those invariants which can be given, can be computed using the resolution graph. And so basically this is what I want to do, some analytic invariants on the resolution or topological or combinatorial invariants of the resolution graph. And actually, today I will assume that the link is rational homogeneous. That means that the resolution graph is a tree of rational curves of pi-1s. So what is the main question, what I want to discuss? And then that was basically the main motivation of say, the analytic lattice cohomology. But step by step, we have to arrive first to the topological one, and after that, the analytic invariants. So I consider this link, that is a three-manifold, or I consider combinatorially the resolution graph. And we know that recently, yes, in the low-dimensional topology, we have a lot of very strong, very important invariants, also numerical invariants of three-manifolds. So one of them is the Seiberg-Witten invariant. For example, if it's integral homology sphere, then we have the Casson invariant, which is associated with the fundamental group. But the fundamental group and some numerical invariants are very, very strong invariants. But what I would like to discuss here, some cohomology series. So there is a new series, the Hegar-Fleur homology associated with the three-manifold, or the embedded contact homology, or there are some other versions of this homology series associated with three-manifolds. So that is my question now, that if we have this, if we have in mind this cohomology series associated with three-manifolds, and we know that the link of the singularity is a three-manifold, then how we understand these invariants, how we understand the Hegar-Fleur invariant or the Seiberg-Witten invariant, yes, but basically the cohomology theory, the Hegar-Fleur cohomology in terms of singularity theory. And even more, so I want to do the next step, that we know that we in singularity theory we put in pairs this kind of invariants. We have the topological versus the analytic invariants. So if I understand the Hegar-Fleur, say as a topological invariant in terms of the link, then what is its analog as an analytic invariant? If I can somehow define some cohomology theory which is associated with the analytic type of the singularity, which is somehow, it's in many good cases say it coincides with the topological one, and but somehow it describes also the analytic type of the singularity. So these are the main questions. So for this, I want some short introduction of the species. It's actually, I don't want really to speak about the species structures of the link, but why is this important? So for example, if I want to understand the Seiberg-Witten invariant of the link, so they are indexed by the species structure of the link. And if I want the Hegar-Fleur cohomology of the link, they are again indexed. There is a graded decomposition, and the grading are indexed by the species structures. Actually, I don't want to enter too much about this structure, but what is important for us that this species structure of the link is actually in H1 of the link torso. So H or H1 of the link is a finite group because we assume that it's an integral homology sphere, it's a rational homology sphere. So in that case, this H1 is a finite group, and the species structures are indexed by this group. Actually, if it's integral homology sphere, then there is only one species structure corresponding to the trivial element of the trivial group, and then we are happy. But otherwise, we have a finitely many objects, say, which are indexed by this H1. So I will not say anything more about this species structure, but what I want, I want some object, or I want to generalize some cohomologies which are indexed by the each one of the link, and this will be denoted by H. And there are also some, yes, nice canonical choices of this element, but doesn't matter. What is important that you see that for each spin-C structure or for each element of the H, I will have the Seibertwieten gives a rational number, and for each spin-C structure or for each element of the H, I will have a cohomology theory. Immediately I will tell you, actually it's even written here, that they are Z graded ZU modules. So that is the cohomology associated with the sigma spin-C structure. And what we know that the Euler characteristic of the cohomology theory is the Seibertwieten invariant. Yes, and the question is again that what is the pair? Say what is the analytic pair of this object associated with the analytic type of the singularity. So let's see first that what is the analog of the Seibertwieten invariant. Yes, so now we have a numerical invariant, the Seibertwieten invariant associated with the link, and we have a cohomology theory whose Euler characteristic is the Seibertwieten. So let's step by steps to see, so what are the analytic analogs. So if I have a resolution, then I can consider each one of the structure sheaf. That is a geometric genus. So that is analytic invariant. And of course, that is, if I know the topological type, then I have some bounds, but usually it's not topological. If I fix the topological type, each one might jump. So it really measures the analytic structure on the fixed topological type. Well, what do we want? We want the H index version of this. So what is H? H is exactly the H one of the link. So usually when we want somehow, I have an invariant associated with the singularity, and I want somehow the analog of it, generalization of it, which is indexed by H one of the link, then we go to the universal abelian covering. So in this case, we consider from pi one of the link to the H one of the link, the natural epimorphism that gives a normal surface singularity, the universal abelian cover of X, that is denoted here by XA, and we have a natural Galois action of A on XA, and then this is compatible with the resolution. So I can consider here the resolution of XA, which is compatible with the resolution of X, and then we consider each one of X tilde A, yes, of the structure sheaf of that. On that we have a natural decomposition, eigenspace decomposition. So each dimension there has some dimension, so that somehow the Galois decomposition or the eigenspace decomposition associated with the universal abelian covering gives a package. It's different numbers, the equivariant geometric genus, which is indexed exactly by the Galois group, which is the H. So in this way, we consider we have automatically or by this construction several, yes, numerical invariants, the equivalent geometric genus of A, which is indexed by our group H. So this is what we want to lift now to the cohomology theory. So what do we exactly have? So we have in the topological side, which is on the right hand, the Seibertwieten invariant. The Seibertwieten invariant is for each H, I have a number. On the left-hand side, I have the geometric genus indexed by H. That is the equivariant geometric genus. And actually, it's in the last decades, there was several theorems which connects this, that indeed, this is a good pairing. In the weighted homogeneous, rational, elliptic, and many nice cases, they coincide. So that is a good start, that they, in nice cases, coincide. Maybe when I have a variation or I have bad, say, analytic structure, then they are not the same. But that's exactly the point. That no, we know that for the Seibertwieten invariant, we have the Hegar-Fleur is a categorification. What is the meaning of that? That there is a HF plus is the Hegar-Fleur cohomology, is a cohomology theory such that its Euler characteristic is the Seibertwieten invariant. Now I know that from analytic point of view, the analog of the Seiberwitten is the geometric genus, the equivalent geometric genus indexed by H. And I'm asking here, that is the question mark here, that how I can construct some cohomology theory in such a way that that cohomology theory gives, yes, it's the Euler characteristic, exactly the PG. So that is the, say, the plan or the main question. And of course that we would like also to have some relationship between the analytic and topological cohomology theories. Well, so this we will do in 2 steps, because it's Heger-Fleur, and actually I will say absolutely nothing about the Heger-Fleur, but that's exactly why I want in 2 steps. First, so the Heger-Fleur is a categorification of the Seiberwitten. And actually, using singularity theory, just a resolution graph and this construction, I will construct a topological lattice cohomology associated with the singularity, with the link of the singularity, or with the resolution graph, whose Euler characteristic is the Seiberwitten. That is the first step. This is no analytic version here. Just the topological HF plus will be replaced by a topological lattice cohomology. This is, maybe you heard about, I gave many talks about this. And actually, even this talk I presented already at Miami conference, so I apologize if somebody already heard, but I saw that this is an important subject, and I will repeat. So the first step is that at the topological side, we define the lattice cohomology associated with the resolution graph. And after that, on the same, somehow similar construction, or on a similar way, somehow using, instead of the link, the analytic type, we will construct on the right-hand side what I have, the lattice cohomology, analytic lattice cohomology associated with the analytic type. So the first is basically the topological lattice cohomology, and after that we go to the analytic one. But basically the construction is more or less is the same. In what I mean by this is the same, that there is a very general construction which gives a lattice cohomology associated with a weight function. And if we take a weight function topologically, a nice one, a good one, then I will get the topological lattice cohomology. If I take a different weight function given by analytic invariance, then I will have the analytic lattice cohomology. So that is the general construction of a lattice cohomology. We will start with some combinatorial setup, a lattice and a weight function, and then choosing different weight functions, we will have different cohomology series. So what is exactly this combinatorial construction? So what do we need to define a lattice cohomology? So we need a lattice. Actually, this is, yes, what we need, a lattice ZS, and actually even a fixed basis. That is very, very important, not just an abstract free Z module, but with a fixed basis, EV. That, in our case, this will be the lattice generated by the exceptional curves in the resolution, or a plumbing graph associated with the Plumb-3 manifold. And the vertices are the fixed basis. So that is what we need. So this is, in our case, it's okay. We have it, and it's, I don't say that it's an easy object together with the intersection form, but it's okay. It's an easy object, basically. And what we need, it's a weight function. For these weight functions, for each lattice point, I need a weight, which is an integer. And I need also some finiteness property of these weight functions. So here you see that basically that for n very small, I don't have any lattice point with weight n. And if I fix any n, the number of lattice points with weight less than n, it should be finite. So in many cases, this weight function, it can be, or in the topological version, is a quadratic function. It's a positive definite quadratic function. So in the left-hand side here, you see I wrote that L is our lattice associated with the exceptional curves, and here is the Riemann-Roch function. So on this, on the intersection matrix of the resolution graph, it's negative definite. So if I take here negative 1/2, that is just because the Riemann row, but L intersected with L, that is the quadratic part, that is a positive definite quadratic function. So if I think about this as a real quadratic function, then that is a compact ellipsoid. The level sets are compact ellipsoids. So inside of a compact ellipsoid, I have finitely many lattice points. So that is exactly somehow the analog of, or this, in this case, that shows that in that case, this finiteness property is satisfied. So we need for the cohomologies to have some finiteness property of the weight function. And even we see here that this is a good example when I consider, say, a Riemann row function, where this K can be any characteristic element, can be also the first-chain class of the canonical, of the canonical class, can be also the canonical class of the resolution. So out of this, the lattice with the fixed basis and the weight function, we want to construct a cohomology theory. For each Q and HQ, and each HQ is a graded ZU module. So it even has some extra graded properties, which is the property also of the monopole cohomology, of the Hegel cohomology, of the all these modern cohomologies, recent cohomologies of the three manifolds. So what is the construction? So we have to make a cubical decomposition of the real space. So S is the dimension of the lattice, the rank of the lattice. We consider the real space, and we embed the ZS to the RS as lattice points. So we have basically here, so here maybe even, so we have the lattice points in RS. So that is, here are the lattice points, and we have the zero cubes. The zero cubes are exactly the lattice points. So these are exactly the lattice points. The 1 cubes are exactly of this, the natural cubical decomposed lattice points, plus the lattice points, plus some base elements. Here it's very important that we have the base elements fixed, because if I take another one, maybe, yes, some lattice, and this is another base element, that is completely different cubical decomposition we will have. So that is, we want to fix the base elements, basic, and then we have associated with that a natural cubical decomposition. So we have the 0 cubes, 1 cubes, natural 2 cubes. So we have, yes, in 2 direction, the E1 and E2 direction I go, and the 2 cubes. And we have for any subset of, so for the cube, I have to fix this element, the base element, say, of the cube, and the direction, so the subset of the vertices, and then we have the Q cubes. And so this is basically the local neighborhoods of the lattice points, somehow using the base elements, how I can go from a point to the neighbor, its neighbor, and then after that, the segments and cubes and so on and so on. So, and then we have, yes, we have the lattice, we have the weight function for the lattice points, and I introduce a weight function for any cube. The weight function of a cube is the maximum of the weight function of the values of the vertices. So, for example, if this is a segment, then the weight of these segments is max of the value of the left and then the right end. Yes, so this is how we introduce the weight functions. And if we have this, then we consider for each integer n, we consider a topological space Sn. Yes, that is a cubical complex. That is the union of all the cubes such that the weight of the cube is less or equal to n. So what is the meaning of this? So for example, if this W was, the weight was, say, the real weight function is a positive quadratic function, then we have the levels as the ellipsoid. We consider the corresponding to n, the levels at the ellipsoid. I consider all the vertices, all the lattice points inside of the ellipsoid, because they have the weight less than n. And after that, a segment is considered if both endpoints are there, because then the max is less than n. If, for example, I consider this segment and this is less than n and this is outside, then this segment is not considered. So after that, I consider the higher dimension. A higher dimensional cube is considered if all the vertices, the ends, vertices are inside of the ellipsoid. So in this way, I will have a tricky space. It's very interesting to notice that even if the essence, even if the real ellipsoids are contractible, convex, beautiful, nice. This Sn can be non-contractible, can be very tricky. For example, here it's in this picture, I wanted to show something. So for example, if this is the level set here, on that level set, I have two vertices, both of them inside, so they belong to Sn, but I cannot connect them by one edge because this endpoint and this endpoint is outside. So this is, I have here two connected components. If I consider a bigger n, then automatically this will appear there and in the bigger n, so it's changing Sn in Sn plus 1, the topology will be different and in the bigger Sn, I might be able to connect them, but each Sn can be very tricky. Also here, you see that I have here a cube, and if all these vertices have weight less than n, then all these one segments are inside of Sn, but if this one and this one, it's outside, it has weight higher, then I have here a loop in some Sn, which is not contractible inside of Sn. So these spaces Sn are very tricky, and I have this tower of spaces associated for each integer. I have Sn, and I have these tower spaces. So this is exactly the construction. So here somehow what is important, the weight function and the lattice points, how they fit together, how the lattice points, so the lattice structure, how is inside, how it's somehow compatible with the level sets of the weight function. Okay, so let's see, 31. Yeah. So what is the cohomology? The cohomology is that I consider all these spaces as Sn, and I make direct sum over this n as Sn of the usual cohomology of HQ. Yes. So I fix Q, here it's fixed Q, and then we consider for this n, I replace, yes, this Sn is given as a union of Q's with weight less than n. I have a tower of, maybe it's, I didn't emphasize sufficiently that I have this tower of spaces that Sn, yes, this is everything less than n, this is everything Sn plus 1, bigger and bigger, say, ellipsoids, and inside of them we consider the cubes. And then this tower of spaces is replaced by their cohomology, and we consider the direct sum. And of course, that this has a lot of gradings, as a Q grading, that is the usual cohomological grading, but also has this n grading, so this HQ is graded by n, say, that for each Sn, so the increasing tower of spaces. And actually, I have a U action that is usually in the gauge theory, it's used U, and that's why I adopted also, I use this notation here, that Sn is actually belongs, maybe yes, here it is written here, that Sn is a subspace of Sn plus 1, and this gives, you see, this gives a cohomological restriction map from the n plus 1 grading to the n grading. That is a U action of this direct sum. So U has, say, degree -1 in this terminology, and so I have here HQ is a graded ZU module. So that is the structure what I want for any Q. Q equals 0 is a little bit tricky because that is H0 and that is connected component. And we know that H0 has a direct sum decomposition of, when it's not empty, of course, of somehow Z and the reduced cohomology, zero cohomology. And for this, so this is the minimum of the degree of the weight function. Starting from there, I have the tower, it's non-empty, Sn is non-empty. We have the restriction maps. And then this gives a tower of Z's, somehow given a fixed point in each of them, I have this tower. And I have the reduced cohomologies. The point is in this that you see, in this way, in a naive way, I cannot introduce any Euler characteristic because here I have an infinite tower that H0 in this way, has infinite rank. But if I eliminate this infinite Z tower, then what remains, that's the point, that what remains, it has finite Z rank. And also for any Q higher, HQ higher also has finite Z rank. And so Actually, even I mentioned it that in all our cases, when n is very big, then Sn is contractible. So all the information in that for n very big in S H0Z, in that one is eliminated by this tower. What remains the reduced part, and that has a finite z degree. So we can introduce the Euler characteristic of the lattice cohomology, which somehow has this tricky part, which comes from the tower, from the minimum of the weight function. That is the information what we keep from the H0 tower. And after that, we consider for NQ the usual, yes, definition of the Euler characteristic from the reduced part, the alternating ranks or sum of the ranks of the HQs. So this is somehow the definition. If I have a weight, if I have a lattice, I have a weight function, then immediately we have lattice cohomology, and we can define also the Euler characteristic. So that was a general construction. So let us say the topological version. What we have when I have a link of the singularity? I have the resolution graph, so I have a resolution. I have the exceptional curves. That defines the lattice. I have a natural basis EV that is given by the exceptional curves, so that is the basis. I have an intersection, negative definite intersection form. So that is what we have from the resolution, from the topological, or from the, yes, the resolution, combinatorics of the resolution. I can even take a characteristic element that's defined in this way. Is not so important. We can take, for example, the canonical, the first chain class of the, yes, here it is the canonical cycle, the first chain class of omega of the top cohomology, or top differential forms of X tilde. Then we will have the canonical lattice cohomology. But you can take any characteristic element, and then we consider this Riemann-Roch expression. So this is the intersection form, and we have -1/2 of L. That is actually will be an integer because of this characteristic element. By the junction formula in the case of C1, we actually is easy to verify. So that is no one weight function. That is the topological weight function. For lattice point L, we have this weight function given by, say, the Riemann-Roch expression. And actually for any H, you can take a very canonically, it's written here, characteristic element. And if I take that weight function associated with that, then for any H, we have a weight function. And for any H, then naturally we have a lattice cohomology, a topological lattice cohomology, which is a graded ZU module. That is the topological lattice cohomology associated with the singularity, or with the topological type of the singularity. So this was, we have a lot of properties. I will not, so that was defined in 2005, 2008, in several articles. First, just the canonical one, after that, indexed by H, indexed by all spin C structures. What is important, then the Euler characteristic is exactly the Seiberwitten. So that is a good sign that that is exactly what we want. And also there are a lot of properties here, what I will not, let's see the time. So probably I will not mention, but we can characterize using these rational singularities. So for example, X is rational if and only if all the spaces Sn are contractible, elliptic ones, then again, and then so several characterization of families of singularities. And also there are a lot of algorithms how to compute. Maybe one more remark here. Probably it's not mentioned here, and but what is important that you see in the case of yeah, maybe yes, sorry, here it is yeah. So here in this definition, I use the resolution graph. The resolution graph depends on the chosen resolution. Well, one can show that this object is independent of the resolution. If you take a different resolution, then this lattice cohomology is the same. So this means that it's an invariant of the three manifold of the link. So it doesn't matter what plumb three manifold I take. So if I blow up, blow down something in the resolution graph, then I will have the same object. So that is an invariant of the three manifold, independent of the resolution. And of course, it gives a lot of nice properties about the link or about the topological type of the invariant of the singularity. Even here, I mentioned historically some results that indeed this lattice cohomology coincides with the Hegel-Floer cohomology of Oswald and Szabó. Actually, the very last step was proved in 21 by Zemke using some spectral sequences, and by some particular cases was previously proved, but very recently was proved that this is indeed the Hegel-Floer. But what is now for us is important, that what we have a topological Seiberg-Witten numerical invariant, and we have a categorification. We have a topological lattice cohomology whose Euler characteristic is a Seiberg-Witten. On the other hand, on the horizontal side, Seiberg-Witten somehow I can connect, or I believe that it can be connected, or the analytic analog of the Seiberg-Witten is the geometric genus, of the singularity as an analytic invariant associated with the structure sheaf H1 of the structure sheaf. Even I have again here somehow both of them are indexed by H1 of the link, so we have an H invariant equivariant version of both of them. And now the question is that what we should put here, how we have to define the new analytic invariant, the new cohomology theory, whose Euler characteristic is, say, the PG, and somehow which can be connected also in some cases, or in some nice cases is really the topological one, and also in the, say, ugly cases, when I very badly say the analytic type of the singularity, then I really, this cohomology measures, so C is the analytic type. So I fix the topological type, and I consider a variation, or I move different, I consider different analytic structures, then these objects hopefully sees also this variation of analytic structures. Even PG, we know that jumps when I can jump and I move the analytic structure. So what is this construction? So this is analytic lattice cohomology. This is a joint work with Ágoston Tamás, student of mine. So again, I start with a normal surface singularity. I have the link. The link is a rational homosphere. Again, we assume this. So this means that the resolution graph is a tree of rational curves. And our goal is that to define an analytic cohomology theory whose Euler characteristic is a geometric genus. Here I will do only the canonical one, which corresponds to the canonical element, the trivial element of H. If we want for all the spin-C structures or all the H, then we have to go to the universal abelian cover and repeat all this construction at the level of the universal abelian covering. That I will not write, I didn't prepare that part, but if you are interested, you can find on the archive article. So here, just the canonical structure, canonical cohomology theory is presented. So again, I start with X, I consider a resolution, and now we want what we need. If I have a resolution, automatically I have the lattice. We have again the exception, we have the lattice generated by the exceptional curves. We have even intersection metrics, but that we don't care right now about it because it's topological, and we want some weight function associated really with the analytic type. We want sheaf cohomology, somehow weight function which is given by some numerical invariance given by sheaf cohomology. So we have the lattice, here the exceptional curve, and what do we do using this? That we have the multivariable divisorial filtration. That is the filtration what was considered also by Delgado, Campillo, and Guzenzade, and by many people, and also I use many times this. So this is a filtration. So if I fix a lattice point in the lattice, so that means that I fix a non-reduced cycle supported on the exceptional curve, then I'm searching for, that is L, that I'm searching for functions such that the pullback of the function, the divisor of the pullback, is larger than L. So this means larger means that component-wise. So for AV is bigger than BV for any V. That means that A is bigger than B. So here we basically give the divisor so that I can even use a different notation. It's O of minus L. If that is, it's so that even I can use this one, that O of, yeah, if L is, yes. So and here it's X. Yes, so that is a filtration given by ideas of the local ring. We have, of course, that is a filtration, and we consider the Hilbert coefficients, the Hilbert series associated with this. These are the coefficient associated with L is the dimension of O divided by FL. So this is the codimension of this FL ideal. So that is one of the ingredients, and this is a very tricky invariance. So that really it's a multivariable. So it's, if you have the lattice, yes, you have a multivariable lattice. For any lattice point, you have a HL. You have also, and of course, there are a lot of connections between these HLs and how they increase, but usually it's non-trivial invariant, and it really measures the analytic type. Actually, this is an increasing weight function, so this is not really good. I didn't really emphasize at the beginning that if I consider the weight functions, that shouldn't be increasing. That should be a more complicated weight function. So we have to do something with this. We need another ingredient. So the other function is H1 of the OL. So I consider not the complete lattice, just the effective. So the first quadrant of the lattice, I consider the base elements, and of course that cubical everything. But on this first quadrant, I can define also, that is the scheme theoretical OL, H1 of this OL. That is also an increasing function. H1 of OL is increasing, but actually it stabilizes. When L is sufficiently large, then that is exactly the PG. So that is also related with the geometric genus, and it's a nice analytic invariant. And what we do, we consider the difference. So that is the analytic weight function. So again, we have a lattice with bases. We have a combinatorial decomposition of the, say, the cubical decomposition of the RS, and I have a analytic weight function, or a weight function associated with the lattice point. Then we can consider the weight function of the cubes by max, so max of the vertices, and by the general construction, we have a lattice cohomology. So that is the analytic lattice cohomology associated with the canonical species structure. If we want all of them, then we go to the universal abelian covering. We have the filtration of the local ring of the universal abelian covering, and we have to repeat everything. It can be done. So yeah, it's written here. So this is now what we have, and let's see some properties. I have a few more minutes. Oh, so let's see what properties we have. So again, we have a resolution, and then using this shift theoretical weight function, we can define the lattice cohomology associated with this resolution. The most important, so the very important fact is that is again is independent of the resolution. So if I blow up, say somewhere this X tilde, then that object, of course, that the lattice will be modified, the weight function will be modified, everything will be different, but one can show that all those spaces Sn, so of course that the Sn space is what we define, they also belong to some space which depends on the resolution, but the homotopy type of those Sns is stable. For each n Sn, it's independent. Homotopy type is independent of the resolution. So the cohomology of Sn is also stable then, and that means that this can be defined, the lattice cohomology is independent of the resolution. So this is really invariant. It's invariant of the local germ. For a normal surface singularity, I have HQ for each Q, HQ bigger than 0, and each HQ is a graded ZU module. And again, we have the finiteness properties. We can separate the Z tower at each 0 level. We have the reduced part, and then using this Euler characteristic definition, the natural one, what we have to use in the case of lattice cohomologies, is we have the natural definition of the Euler characteristic of this cohomology theory. And again, it's very important fact that the Euler characteristic of this analytic lattice cohomology is exactly the geometric genus. So that is indeed, it's a categorification, or it's a theory which makes a cohomology theory whose Euler characteristic is the PG. It's a lift of the numerical invariant PG. So that is exactly what we wanted. Again, we have a lot of theorems that somehow characterization. So how I can connect with the classical singularity theory. So for example, here the vanishing of reduced part, it's exactly the rationality, like how it was in the case of topological one. Actually, in the case of rational one, this shows that the analytic and the topological one is the same. So in the rational case, just the Z tower. So each Sn is contractible. So somehow that is rationality. Each Sn associated with the analytic weight function, it's contractible. And also the rational minimal elliptic, again, a lot of families can be characterized. And actually, this is a very new theorem. I don't say that we have many computations, but some of them we computed for weighted homogeneous. We computed, so it looks a good theory. What I would like to emphasize is some properties. So how it behaves with respect to when I change the analytic type, and also how it changes when we deformation theory. Maybe this is a visualization. That is H0, H0. If I want somehow not HQ in general, just H0, that is the connected components of Sn. So in that case, at the n level, that is the n level, I put the connected components of Sn. I put a dot, that means I put a Z, yes, for each connected component of Sn. And these are the inclusions. So that is a restriction induced by the inclusion of Sn. So I have Sn. Sn is included in Sn plus 1. The cohomology gives a restriction, and that is the restriction of the arrow. So somehow we have a tricky graded graph, I call graded root. And these are somehow that it's a good visualization of H0, of the cohomologies. Somehow that's some pattern can happen, some pattern cannot happen in this graded root. But that is a nice, it's not so important, but sometimes it's very easy to make pictures of H0. So here again, I don't want to enter in technical details. What I want just to say that if I fix a resolution if I fix a normal surface singularity, then, and I have the analytic type, I have also the analytic lattice cohomology, and I have also the topological lattice cohomology associated with the link. And the point is, and here it's written somehow, but maybe we don't discuss all the details, that I have a natural map which connects the analytic lattice cohomology with the topological lattice cohomology. That is a graded ZU module morphism. And using this, we can measure somehow when I fix the topological type, then this right-hand side, the lattice homology of the topological type is fixed. And then I can see that, okay, then I move the analytic type. Maybe I have different analytic types. How I see really how that is modified or not. And that is now the next slide. I have here, actually, maybe I go even to the next one. This is for the elliptic one. Already in the elliptic case, we see some modification. For example, in this graph, in this number three, this is a resolution graph. Yes, that is not minimal elliptic. If I delete this last -2, then it's minimal elliptic. In that case, analytic and the topological theory coincides. But if it's not minimal elliptic, then for the Gorenstein case, the PG is 2. For the generic analytic structure, PG is 1. So already at the level of PG, I see the jump. Yes. Then I can ask that, for example, with this topological type, what is the topological lattice cohomology? H0. Then is this picture. Yes, that visualization using this graded root is this one. And if I know I consider the Gorenstein structure, analytic type, then the analytic lattice cohomology is the same. But if I consider the generic one or non-Gorenstein structure, then it's different. And very interesting that here basically you see in this picture, somehow these are connected components. So in each connected component, somehow it's generated by some important lattice point, yes, of that ascent. Here, this is by the 0 cycle. This is the minimal cycle of Artin, and that is the canonical cycle. And exactly in the non-Gorenstein case, the canonical cycle somehow disappears. That is exactly the Gorenstein property. So it's somehow, somehow exactly this analytic structure is very nicely measured by the analytic lattice cohomology of the here in the right-hand side. And even, let's see another example. This is this resolution graph here. That is, I can denote also the link in this surgery version, the notation, but actually this is the resolution graph here. This is the topological. On the left-hand side, we have the cohomology of H0, topological lattice cohomology. And actually on this, I have 3 very different analytic structures on this topological type. Actually, this was classified by myself and Okuma, Tomohiro Okuma, because exactly this is what we wanted to see, how the moduli space of the analytic structures, what if we can say anything about it. And this is a complete intersection. Actually, it's a splice type complete intersection. It's a Gorenstein. It's a Kulikov non-Gorenstein, and also generic analytic structure. Here in the first, PG is 3, here the PG is 3, and the last one, PG is 2. And here are the graphs or the graded roots of the analytic structures. And it's very interesting. You see that again, I have here the different minimal cycles, the topological side, the minimal cycle, 2 times the minimal cycle, the canonical cycle, they generate the topological one. And the maximal ideal cycle, that is the smallest, yes, when I go to the analytic type, then the maximal ideal cycle measures the simplest functions, yes, and that is the 2 times the Z mean in the Gorenstein case. So somehow the Artin cycle is not analytic cycle. Well, it disappears somehow. In the case of Kulikov, the maximal cycle is the Artin cycle, so this appears, but it's non-Gorenstein, so the ZK. So this disappears. And the generic analytic structure, also the maximal ideal cycle is large. It's not the Artin cycle, and also it's non-Gorenstein. So ZK is not analytic. So again, here 2 legs are missing. So somehow already already this A0 measures, and the lattice analytic lattice cohomology somehow measures very nicely the variation of the analytic structure. So I think that I have to stop. Let's see. Yes. I have also some other theorems, how it's conjectures, but I don't have time. No, about the deformations, that how the stability is respect to deformation, and that those are really beautiful conjectures, but it's less results, more conjectures. So it's maybe I speak about them some other time. So thank you very much for
Professor Némethi, if you want, you have more 10 minutes. It's no problem.
More, yeah, I see. Yeah, but maybe it's not my time because I just okay. I can okay. So let's okay. Thank you for in a few minutes. I can. Okay, so this is the so you see here what we have. Yeah, just what I was able here to show. That this is, I have a natural map which connects the analytic and the topological one. But what I expect that this is injective, but it's still, we have to prove it. So this is a conjecture. So this is here the conjecture. that indeed the analytic lattice cohomology injects as a graded ZU module in the topological one. So in this way, somehow some graded ZU submodules of the topological lattice cohomology measure somehow some discrete stratum of the strata of the moduli of the analytic structures. So this was basically one of the main motivations, that I want to see the moduli space, even maybe a parameter space of the different analytic structures on a fixed topological type, where this can be a good, say, invariant, which is not just a number, it's more complicated, it's graded ZU modules. And in this one, if we can somehow codify the stratification, nice stratification of the analytic types. And actually that would be a goal, to characterize, say, blindly or topologically, or somehow, not topology, but using singularity theory, all those ZU submodules which can appear as analytic graded ZU modules, analytic lattice cohomologies. So let's go to the deformation. So again, everybody knows what do we mean by a flat deformation. And of course, that when we consider flat deformation, so sometimes we consider some restrictions. So sometimes we just say that, okay, I want to consider very general flat deformation, but sometimes we consider flat deformations when the PG is constant, or where K squared, that is the canonical cycle, when K squared is constant, because they are related. You see that K squared constant means exactly that we have a weak simultaneous resolution. That was Laufer's result, yes? And then if we have a very weak or some kind of simultaneous resolutions, then we hope that, and then it's much easier, or we can connect the different lattices. So that's why sometimes we wish, or we hope that using some rigidity of this type, some constant values along the deformation, then we hope that we can have stronger results. So what are the conjectures here? That about the topological one, that if I have a K-square constant flat deformation, so that means that we have a very weak simultaneous resolution, then the topological lattice cohomology H0, that is topological lattice cohomology, is constant. So along such deformations, this is not modified. And actually, I want just to emphasize that here the resolution graph, the lattice, everything jumps. So it's not this. So it's also the link, everything jumps. And somehow, and in many examples we check this, and in some cases we prove that this is really true. And this would have also strong consequences in the deformation, how we connect, say, Heger-Fleur with the deformation theory. And these are exactly, so maybe, yeah, a few more words. So in the Heger-Fleur theory, we have good functors given by cobordisms. In the topology, in the lattice cohomology, still this is somehow, we have to still work on it, that what are the good functors. So probably the good functors are given by deformations. So that's why we really have to study next the relationship with the deformation theory. And so let's see, yes. And here, this is actually, it's one example here. It's that written that, you see, I have here deformation, even in C3, it's hypersurface jumps. And here we see that the linkage jumps, the intersection matrix jumps, the Riemann-Roch formula jumps, everything jumps, but PG is constant, K square is constant, and actually it's also the lattice cohomology is constant. Yes, and somehow I missed, yes, here it is, the conjecture here not up, yes, that with respect to analytic lattice cohomology, so what we expect that along a PG constant flat deformation, all the H star analytic is constant. Yes, sorry. So this was this picture. And But of course, that these theorems, it's I don't claim that they are very easy to prove, but this is the next steps to study this, the connection with deformation theory. So yeah, and yeah, several properties, reduction theorems about both of them, how to compute. So there are some algorithms, how to reduce to the less, the rank of the lattice we can reduce. That is actually, these reduction theorems already exist, and we can do this. And yes, this is other dimensions. So the curve case, or the higher dimension curve case also is done. You can check on the internet, but probably I will not discuss about that. So thank you very much for the
Thank you for the very nice talk. So there is some question for the Professor András. Maybe then the people online.
I have a question.
Yep.
Thank you, András, for the nice talk. I was not completely sure I was going to ask you, but I think from your last example, analytic equivalence and topological equivalence, or analytical type and topological type, you take into account the ambient, right?
Actually, it's not. No, not. Yeah, maybe this is confusing, this example, because that is in C3. But this is also in the topological type. I consider only the link, so the abstract topological, so the I don't consider even if I consider topological case, then just the three-dimensional link and not the embedded link. So even if it's not hypersurface, it is runs. So we can discuss this for any normal surface singularity, even if it's not hypersurface. And also the analytic is just X, not how it's embedded.
I see.
But it's, you see, your question actually is very deep, actually, because it's very interesting. Because if I, for example, if I take a hypersurface, then I really hope that this information, the abstract, say abstract lattice cohomology, abstract, say analytic lattice cohomology is related. You see, the other characteristic is the PG. Yes. PG is the number of spectral numbers in the first interval. But the spectral numbers, somehow, that is a Hodge theory, that is the vanishing cohomology of the embedded analytic type. And actually, we can recover in the weighted homogeneous case, in the hypersurface weighted homogeneous case, we recover somehow some information also about the embedded analytic type. But really, the definition is just the abstract one, non-embedded. But if it's hypersurface, I think that it contains a lot of information how it's embedded also about that.
Yeah, I see. So even if you, in general, the results, they don't give information about the embedded dimension, right? In general.
No, yes. Actually, actually, I'm hunting for that if from this information we can find the embedded dimension. That is a very, very important, very interesting question. What is the embedded dimension if this information contains the embedded dimension? That is, that would be very, very interesting. And also this multiplicity embedded on all this, it would be, or the Hilbert, yes, the Hilbert function associated with the maximal ideal filtration. That would be very, very interesting.
Yeah, the second question is somehow related with this, because the question is, if you restrict to some special classes of surfaces, of normal surface, perhaps you can say more. I mean, you gave several applications, right? For instance, if you restrict to the class of determinantal surfaces, right? And you take the formations inside this class, Right.
Yeah.
So
It would be very interesting. I think that in any case, when you have some very nice combinatorics or very nice structures somehow, yes, this is determinable, that should give some very specific nice properties. And I would be happy to work on or to discuss with anybody this. And if you have nice deformations, again, probably that those deformations will be some stability or some nice functors. Or yeah, I agree with you, but I don't know what to say, because this is a very new theory, this analytic part. But even in the topological part, the deformation part is still, it's not settled completely. But I would be happy even for topological, or in any case, to see some of that. If somebody comes that, okay, I would like to see these families and let's see how it is, I would be happy to work on it. Yeah.
Thank you. Thank you very much.
Sure.
Okay, more questions?
Hi, I would like to ask you something related with deformations. So
Yes.
you hope this cohomology will answer some questions about deformations with some topological invariant fixed. Okay?
Yes.
So my question is, since you are considering links, if you fix, for instance, some Lipschitz invariants, can this cohomology tell you something of deformations with some Lipschitz invariant fixed?
Well, this is again very nice question, and I don't know. So that is between these two. You see, that is between the topological and analytic. So it might happen that there is a third version of the Lipschitz lattice cohomology, which is between them. That is the first answer. Maybe it was not exactly the question, but that might happen, that there is here something. And also, it really can happen that some Lipschitz analytic invariants, so that those abstractions appear also here. So the behavior of these objects with respect to deformation is very, very, very nice, very hard, and contains, you see the structure. That's why it's not just a numerical invariant that say PG or some, but it's very rich structure, these ZU modules. And then just one lattice point somehow on this module structure. So the generator of the cohomology moves to higher degree or something. It's modified. So it's a rich structure which might be able to measure very tricky, very, very, very nice deformations. So and also it really measures analytic type. So it can happen that you recover here, or you can recognize here some Lipschitz type. Again, the same. I would be happy if somebody would work on it, or if I can work with somebody on it. So it's a very nice, and I think that very important. And really, you see, this is it's a new object which for the adjacency problems can be, actually that's what we try to apply for agency problems, which is a very hard and very, this is a good possibility, because it's the invariant is a rich invariant and has to do something with deformation. So I think that, but of course, and probably, you see, I didn't check the Lipschitz, or not the Lipschitz connections, so that how, but if you have some good examples in mind, that let's see this deformation, and you would like to see that deformation, that these measures or not, we can discuss that. Okay, let's see those pair, that deformation, and compute both for T0 to T non-zero, and we check that if we see the deformation or not. That would be a good starting point. Yeah, so that is what I can say.
Okay, thank you, and thank you also for your nice talk.
Yeah, sure.
Okay, if there is more question, let's say thanks the speaking again, please.
Okay.
Okay, we're back in the afternoon and then the 2 hours PM. Bye, everyone.